Previously on Physicsball Z, our heroes categorized the different energy resources into either renewable or non-renewable, and after acquiring the multiple infinity slides that they eventually found the different energy resources in, they were attacked by this past paper question. But by using the powerful highlights and the mark scheme, our heroes were able to pattern the full 4 marks. And now, our heroes must swim up the electrical current and overcome the resistors to progress to the next stage. Will this charge end in victory, or will the challenge be too shocking? Find out in today's episode of Physicsball Z. Here are the retrieval questions for this lesson. You know what to do. Tides are caused by the moon. Generators generate electricity. The longest stage of the cell cycle is interphase. Veins have valves to prevent the backflow of blood. Electrolysis is the breakdown of a compound using a direct current. And sublimation is a change from a solid into a gas. Here are circuit symbols that you need to be able to memorize and identify. See if you can name all of them. One is an open switch, then we have a closed switch. This one here is a cell, and when you have more than one cell together, that's a battery. Then we have a diode, resistor. When you've got the resistor with the arrow through it, that's a variable resistor, which means you can change the resistance. Then we have a light bulb. When you've got a resistor looking thing with a fuse inside it, that is a fuse. Obviously this is a voltmeter, an ammeter. These next ones are usually the harder ones. This one here that looks like a variable resistor, but the arrow is not an arrow, it almost looks like a reborn night tick. That is a thermistor. When you've got arrows going into a resistor that's got a circle around it, those arrows are representing light. So light is hitting that resistor. That's a light dependent resistor, or LDR, light dependent resistor. When you've got light coming out of the circle, and inside the circle we don't see a resistor, it's a diode. So this is a light emitting diode, or LED, light emitting diode. Let's first go through exactly what electricity is. Around your room you've got wires all around the place, and almost certainly the metal inside all of them is copper. As we saw before, metals have metallic bonds, which are electrostatic attractions between metal ions and delocalized electrons. Normally these electrons are moving randomly in all directions, but when we connect the wire in a complete circuit, the electrons start moving in unison. If you look carefully, you see that the electrons are charged, negatively charged. Whenever you've got a flowing charge, you've created a current. So a current is defined as the amount of charge flowing per second, and this is measured in the unit called amps. Scientists measure the charge of a particle in something called coulombs. This means that current is the charge flowing per second. This is one of those equations that you do have to memorize. So current is charge flow in coulombs over time in seconds. Here's a past paper question that will help you apply the equation that we just looked at. Try and collect the 2 marks here. The current is 0.6 amps, the time is 300 seconds, and we're trying to calculate the charge flow. We need to rearrange this equation to get the charge flow. So charge flow is equal to current times time. We sub in our numbers, and that gives us 180 coulombs.
Yo, why is the current moving in the first place? Like, what's making them electrons move in the first place?
That's all got to do with something called the potential difference. Before we knew about atoms, scientists thought about charges moving as positive charges, moving from the positive side of the battery to the negative side of the battery. This is called the conventional flow. However, we discovered the electron after J.J. Thomson and realized that the electrons are actually negative, so they're flowing from the negative end to the positive end. This is known as the electron flow. To proper deep this idea, let's use an analogy. In the same way that electrons flow from the negative to the positive end of a battery because there's a difference in electrical potential energy, a skier skis from a region of high gravitational potential energy to an area of low gravitational potential energy because it's moving due to the force of gravity. The skier is representing the electrons and the slope of the mountain is representing the potential difference from the battery. The movement of the skier is the current, because remember, electrons are negatively charged and a current is a flow of charge. But what happens to the skier if we change the ice into tarmac? Would the speed of the skier increase or decrease if we change the ground that he's on from ice to tarmac? Obviously, the resistance will increase, he will slow down. So there's a relationship between current, potential difference and resistance. Here are 3 images to help you understand what we just did, and here are 3 challenge questions for you to apply that to. Do your thing. The potential difference is what's moving the current through the circuit. Remember, that was the slope that we saw in the analogy. The current is limited by the resistance, and in our analogy, that's whether it was an ice or tarmac. The less resistance you have, the less friction, the more current flows. Circuit 1 has a higher resistance because the current is smaller, but the potential difference is the same in both. They both have 3 volts coming from the battery that's pushing the electrons. We can put all that into this equation. Current is potential difference over resistance. This is called Ohm's triangle. Current is at the bottom along with resistance. That means that potential difference is on top. Again, this is one of those equations that you need to memorize. Now we have this past paper question. There's one thing you need to do before putting the numbers into the equation. See if you can clock what you need to do. Here's our equation triangle again, the equation that links current, potential difference and resistance. Current equals potential difference over resistance. Now we need to calculate the resistance from the information that we're given previously. The potential difference is 5.50 volts and the current is 12.5 milliamps. You've probably clocked that we need to convert the milliamps into amps. We do this by dividing by 1000 to get 0.0125 amps. Now let's sub our numbers into the equation to give us this. Rearranging the equation will give us 5.50 volts over 0.0125 amps. And plugging that into the calculator, that gives us 440 ohms. Here's another one. Do you think? We are given the potential difference and the current, so we need to calculate resistance again. This means that we need this equation. Subbing our number in, our numbers go into their location. Rearranging the equation will give us 3.22 volts over 2.18 amps. Plugging that gives us 1.477 ohms. But reading the question again, it wants us to put the answer in 3 significant figures. So we need to round it up to 1.48 ohms. Current potential different graphs have the current on the y-axis and the potential difference on the x-axis. To get the values for this graph, we need to use an ammeter and a voltmeter. When you set up your circuit like this, you can measure the potential difference across a component and also its current, the current going into it. Using a variable resistor means that you can alter the flow of the current through the circuit. If the component that you're measuring is a resistor, you will get this line. You may be asked for 2 marks why this relationship is directly proportional. See if you can collect those 2 marks. It's directly proportional because it's a straight line that's going through the origin. The origin is the 0 point. When you have a component that gives you a straight line like this, it's called an ohmic conductor. The current through a resistor at a constant temperature is directly proportional to the potential difference across the resistor. You need to memorize this pattern associated with a resistor. You need to be able to draw this as well. You've also got 2 more that you need to be able to memorize and draw and also identify, okay? For a filament lamp, which is just a regular light bulb, you have this line. This obviously isn't a straight line, so it's a non-ohmic conductor. The reason for this is that as the current increases, the atoms in the filament lamp vibrate more. This increases the temperature and also the resistance of the current. Think about it. If the atoms are vibrating, the electrons find it harder to flow, which means that your resistance increases and your current decreases. This is actually what happens in the toaster. The last one that you need to be able to memorize and draw is a diode. The line for the diode looks like this. You can see again that it's a non-ohmic conductor and no current is flowing in the negative direction. This is why diodes only allow current to flow in one direction, the forward direction. The reason for this is that the reverse direction has a ridiculously high resistance. The resistance in thermistors decreases as the temperature increases. This is why thermistors are used in things like thermostats. Their properties make them ideal to keep a temperature that's constant or stable within your house, which is also why it's also used as an analogy for homeostasis. Finally, we have light dependent resistors, or LDR for short. They decrease their resistance as the light intensity increases. This is used in automatic lights. It causes them to switch on when it gets dark. And there we go. The mission is complete.
Fatality.
And I'll catch you guys in a bit.